Okay, we'll start. Okay, before we start, is there any questions about anything? All right. All right, so today I want to talk about something called the discrete logarithm problem. And this will be like sort of the main cryptographic assumption that we make for Planck anyways, for the one that we'll be studying. And then later I'll talk about something called commitment functions as well. Okay, so before we start, before we drill down on what the discrete logarithm problem is, I just want to talk about general algorithms. And I'm going to denote it as NGQ. So what do I mean by NGQ? I mean that we're doing things mod P, and we're using a subgroup of the integers from 1 to P, well, to P minus 1, a subgroup that is closed under multiplication. So everything that we worked hard last class to set up, that's what I'm assuming. Okay, so I'm going to show you four things. So I'll have 4 questions for you. For each of the 4 questions, I'm going to give you 2 numbers, x and y, and the question will be to find a third number, which I'll call a. Okay, and in order to answer these, you can also think about that table that I showed you. Maybe I'll copy and paste it in, but you can think about how would I answer the question with the table. So how do I answer using the table? And if the answer is I'm going to scan along a whole row or a whole column of the table and find the answer, that's going to be not efficient. If it's like I can just go directly to the answer in the table, or maybe do that a few times, then it's going to be efficient. Okay. So in particular, we're going to ask about like, do I have to scan the whole table?
Sorry, what's the second one?
What's the second which? Sorry. Yeah. So I'll give you. There'll be a small equation. It'll have an x, a y, and an a. X and y will be given, and a will be the unknown that you have to try and find. Yeah, you'll see it as. Do I have to scan the whole row or column or table? That would be even worse. If the answer is yes, it's going to be infeasible in real life. Once we make P really large, it's not going to work. Okay, let me just grab a copy of the tables again. I will just pull in the GQ, so I won't pull in the whole table of everything in P. Okay, so we have a multiplication table, exponentiation table, and then just draw a line between them so it's easier to see where. Okay, so the questions are pretty easy. So the first question I'll ask you is, say I write down an equation like this: y equals a times x mod p. Okay, and all the numbers y, a, and x are in GQ. Okay, so we're just talking about numbers that are in this table. All right, and like I said, you know what y is, so I'll tell you it's 5, and you know what x is. I'll say it's 13. I guess 5 isn't in GQ in this example, but say it's 4 and 13. And then what I'll ask you to do is find y. Sorry, find a. Okay. So you have one equation, one unknown. You can solve one equation, one unknown, right? Always. There is a solution to it. It's just a question of, like, is this efficient or is it not efficient? Okay. So forgetting about the mod p for a second, how would you solve this if there was no mod p? Yeah.
We'd probably find the inverse.
Okay.
Because we can't divide.
Okay, so you know too much already, but yes. So normally you would just move the x over to the other side,
Yeah.
and a would be equal to y divided by x, right? Okay. So we're going to do the same thing here. I'm going to solve for a, and I'm going to say y divided by x mod p. Okay, do we have division? So one problem is we have integers. So if we, for example, if I ask you what's 3 divided by 2, those are both in GQ, right? So that's valid. I can ask you what 3 divided by 2 is. What is 3 divided by 2, ignoring the mod p? What's half of 3? 1.5, 1.5. Is that an integer? No? We're not going to find a 1.5 here? Okay. So we're going to get in trouble if we start doing division. Okay? But what does division really mean? Okay, let's say I'm holding in one hand, I have the number 3 over 2, and in the other hand, I have 1.5, which is the division of it. Okay, if I multiply those things together, they'll give me 1. Okay, so what division is it's the same as a equals y times x inverse, okay, 1 over x mod p. Okay, and so if you divide by something or if you invert the divisor and multiply, it's the same thing in both math and in, like, regardless of the mod p. Okay, so these two equations are the same. But this we could potentially do something with. Okay, maybe we can find an answer to this equation without involving decimals. Okay? All right, so we have no division. I'll note this on the side. So instead what we do is we invert and multiply. Okay, and sometimes we're lazy and we'll write division anyways. So if you see, there's an encryption scheme called Algamel that's pretty famous. You might see it in 6110. Usually when we're decrypting, we'll just write, we divide this off. In this class too, we'll talk about division. I'm just going to write division. But technically, anytime I write division, I mean you take what's on the bottom, you invert it, and then you multiply it. Okay. Okay, can we solve this equation? So let's pretend this -1 didn't exist. It was just y times x. I tell you y is 3 and x is 10 or 9. Can we solve that equation? We can. We just use our multiplication table. Do we have to scan an entire row? We don't. We can just jump directly to what the answer is. Okay? So this equation is solvable if that pesky little -1 wasn't there, but it is there. Okay? Can I solve just this? Can I write something else instead of x to the -1? Okay, can I figure out, in other words, can I figure out what x to the -1 is?
1 over x.
So it is 1 over x, but because I don't have division, that doesn't get me closer to it. Yeah. So what I want to do is I want to write down a number that is this. So let's be concrete. Let's say it's 6. I don't know. Let's take 16. What's the inverse of 16? Okay, so people say 13. Why? Okay. Okay, so the inverse of 16 is going to be 13, right? Because 16 times 13 is 1. So they're inverses of each other, okay? All right, so what I could do is instead of writing 16 to the -1, I could just write 13. Then y times 13 is mod p, and I'm done, okay? How did I, walk me through, you did it so fast. How did I figure out what the inverse of 16 is? So I scan the row until I hit a 1, and then I look and see what column I'm in. Okay, now, if this table is the size of the number of stars in the universe, can I scan the row until I hit a 1? I can't, okay? A computer can't do that. It's too many numbers, okay? It can do it eventually, but it will take the lifetime of the universe in order to do it, okay? So this way of finding inverses doesn't work. It's infeasible, okay? Is there any other way I could maybe find an inverse? Perhaps that would work. I'd have to think about it, but that's not. There's something I'm thinking of simply. So I'm not using an algorithm. I'm going to manipulate the numbers a little bit. Yeah.
Starting from the 1 and then going that way.
Okay. So it is starting with the mod, but what's the second part?
Starting from the 1, x. We have a z that times x minus 1 would be 1.
X times -1?
It is x times -1.
Sorry. This I'm not sure what you're saying exactly, but
I'm saying this times the inverse of it would be 1. So
yeah, that's right. Yeah. Yeah. So x times x to the -1 would be 1. Yeah. So which is sort of what we did here, right? So we tried to find the number that would give us 1. Yeah. Right. But this algorithm won't work because we have to scan the table. Yeah. Any other guesses? Yeah.
There's another way, like first line it's the mod, second line is the numbers, and I divide it and add the elements, and I have to complete something. I forget it's
Okay. Maybe it sounds too complicated. What I'm looking for is simpler than that. Okay. Let's just zoom into this. X to the power of -1. What other table do I have? So the multiplication table is not going to work for me. I have an exponentiation table, right? Can I just look up x to the -1 in the table? So if I want 16, right? Can I just go up here and find -1, and then I can look up the answer? So I can't. There's no -1. Okay, so I'm stuck. But if there was a -1, that would work. Okay, why is there no -1 up here?
because we are mod q.
So all these numbers are mod q. Okay? So what I could do is, am I allowed to do this? Am I allowed to do that? Okay, can I do a modulus up in the exponent? I can, right? So that's like the Fermat's tiny theorem or whatever it's called. Okay, so but when I move up a level, the modulus gets smaller. Okay, so when I move up a level, it becomes -1. And I can go up another level, which we will do soon. But for now, we just have to go up one level. Okay, so if I can reduce this equation, then I can make some progress on it. Okay, what is -1 mod q? Okay, not in concrete numbers, but here it is 10. That's correct. And in symbols, okay, what's special about 10 here? It's the last column. Okay, is it always going to be the last column? It is, because if 0 is the first column, if I go -1, I go to the column before it, I wrap around, and I end up at the last column. Okay? So this will always be the last column. And the last column itself will be q minus 1. Okay? That's the number. So q in this case is 11. 11 minus 1 is 10. So that's why it ends up being 10. Okay. Can I solve this now? I can. So I do x to the q minus 1. So I just go to the 10th column. And so let's say I want to do 16 and I want to invert it. I go to the last column, it's 13. Okay? And that's the same answer, note, that we got here. Okay, and I promise you that if you check all of the inverses, this will be the column of inverses. The difference is here I had to scan along the row until I hit a 1. Here I can just jump directly to it. So I know what q is, so I can just do a single exponentiation and I get the inverse. Okay, so I can solve this equation for a. I can figure out what a is. It costs me 1 lookup in my exponentiation table. And then once I get the answer here, then I'm going to do 1 lookup in the multiplication table to multiply these two together. Okay, so I can solve with 1 mod exp. That just means modular exponentiation lookup. And then 1 multiplication. Okay, so let's just do an example. Okay, shout out 2 numbers that are in GQ. Just shout something out. One of these numbers here. 8 and it's not hard, just pick one, shout it out. 4, thank you. All right, 8 and 4. All right, so 8 equals a times 4 mod p. Okay, how am I solving this? I'm not going to solve it, you're going to solve it. So I'll sit here as long as it takes. What is a? I want to solve for a. Say it louder.
No, what is p?
Mod p.
What's the value of?
Yeah, p's, yeah, okay, let me just back up and say, these tables here are for p equals 23 and q equals 11. Okay, so these tables are for that, yeah. So here, I can write in, if it helps, I'll write in mod 23. Okay, so, I don't want the final answer. I want to walk through. I want to walk through the whole calculation. So what's the first thing I do?
8/4
Okay, so say it louder. Sorry. A equals 4.
For in
8/4.
Okay. Yeah, sorry. I see. Okay. So A equals 8/4 mod 23. This was a bad example because you can actually just solve it in your head, but we're going to go through the long way of solving it. Okay, this is the same as 8 times 4 to the negative 1. Yep. All right. This is the same as q minus 1. Q's 11 minus 1 mod 23. This is the same as 8 times 4 to the 10 mod 23. Okay, now we got to start using our table. So what's 4 to the 10? So which table am I looking at? Am I looking at the multiplication or the exponentiation? Okay, and so I have 4. I want to raise it to the 10. What's the answer I get? 6. Okay. So 8 times 6 mod 23. Now I want to figure out what 8 times 6 is. Which table do I want to use? Okay, so I have 8 times 6, and the answer is 2. Okay, now I want to check just one last thing. I just want to check and make sure it's right. So if it's right, if I put in a 2 for A, then this equation should hold, right? So 2 times 4 should be A. I can check that here. So 2 times 4 is 8. So that looks good. Okay, yeah.
Are we allowed to do the division there, or?
So I wrote it down as notation, but you can't divide. Here it worked because 4 does cleanly divide 8, but you're going to hit a lot of cases where if this is any other, like not a perfect divisor of this, it's not going to work. Yeah. But if it is a perfect divisor, you could skip all of the nonsense and just write the answer in. Yeah. Okay, questions about this? Okay, what does this tell me? This tells me that I can do multiplication, I can do exponentiation, I can do inverses, all efficient. Okay, those are all efficient operations when I'm working in GQ. Okay, so anytime I'm doing one of those things, I don't have to think about, is a computer going to run out of time doing one of these things? Okay, yeah.
So like all of this is assuming that we have access to the tables, right?
So yes and no. So you like on an exam or something, it would be assuming you have the table. And then for a computer, you have an algorithm that will compute a multiplication or an exponentiation for you. So it's an efficient operation. Even if these numbers are huge, you can do it. Yeah. I won't go into like the algorithm itself, but multiplication is just, you do long form multiplication, but as you're doing it, you just keep modding it down. For exponentiation, what you do is you multiply it by itself, but you have this trick where, let's say I want to compute x to the 4. Actually, let's say I want to compute x to the 8. What I can do is x times 8x, that gives me x squared. Then I can do x squared times x squared, and that gives me x to the 4. Then I can do x4 times x4, and that gives me x to the 8. So I can get to x to the 8, instead of multiplying it out by 8 times, it just takes me 3 times. And then you can get to like big numbers really fast. Yeah. And then there's even more like complicated things that you can do to make it even more efficient. But exponentiation is just multiplying it by itself. That there's no better algorithm, but you can sort of cluster, once you build up some multiples, then you can start multiplying those by themselves and it gets faster. Yeah. So that's relevant when we do this over elliptic curves because there is no exponentiation. You just have an operation and you have to repeat it a whole bunch of times. But yeah. Okay. That's fine. Okay. So we're good with this question? All right. I'm going to show you basically every combination. So every equation is going to look almost the same. All right. So the second one is y equals x times a mod p. Now you might think, oh, that looks the same. But what I did is I swapped x and y. Okay. So now y is here and x is here. Can we solve this equation? Okay, everyone seems to think yes. We can use the same method, right? We relabeled x and y, but mechanically it's the same. What this tells me is that multiplication is commutative, meaning it doesn't matter the order that you do. Or maybe it's associative. There's a bunch of like different terms that mean things, but basically the rules of multiplication still apply. So things like, x times a plus b equals xa plus bx, like all of these like little rules that you don't even think twice about, they all apply. Okay, so rules work the same. Okay, and so we can solve it the same way. Okay, y equals a to the power of x mod p. Okay, so forget about the mod p for a second. How would I solve a if we didn't have this mod p?
Take the log both sides.
Okay, so I could take the logarithm both sides. What would I take the log base? What would the base of the logarithm be? Not in concrete numbers, just in symbols. Is it base y, base a, or base x? It would have to be base a, otherwise I wouldn't get rid of the exponential. So we can try that. So log base a of y equals log base a. Sorry, no, you were right. You said, who said x? Oh, no. Of a to the x, right? Okay, does this help me solve a? It doesn't. My a is just now in the base of a logarithm. Okay, so it's not going to help us. Other ideas? Okay, I'll give you a hint. Let's think about concrete numbers. We'll do 8 and 4 again. So 8 equals a to the 4. How would you solve that for a? No mod p, nothing like that. Okay, everyone's looking blank, so I'm going to help you. I'm going to make it 2 instead. Okay, square root. Thank you. Okay, so a would be the root base, or root, the squared root, the second root of a. Okay, here a is going to be the fourth root of a, right? And so what would I have here? Okay, so I'll have a equals the x root of a. Thank you. Okay, do we think we can just compute a root? What happens if we just compute a root and then we do mod p? We're going to run into the same trouble, which is it's probably going to end up being a decimal, not an integer, and then we can't do anything about it. Okay? So what I want to do is I want to compute a discrete root. Discrete just means keeping it within the integers and not messing around with decimals, okay? So for the same reason, this doesn't work directly, but is there another way we can represent this?
We can make a equal to y to the power 1 over x.
Okay, perfect, thank you. All right, so what we could do is I can rewrite this as a equals y to the power of 1 over x mod p. Okay, first off, this is the same thing, right? We all agree? Okay, so if you want to do a square root or you want to raise something to the power of 1/2, it ends up being the same thing. Okay, so this is math. So this is great. Okay? All right, now the next problem I have is what do I have here? What is 1 over x? Okay, so this is a division. Do we have division? We don't have division either. Okay, so I tried to turn the square root into an exponentiation. Now I'm stuck with division. So what do we do with divisions?
X to the power minus 1.
Okay, so we do inverses. So I invert and multiply. So I can do 1 times x to the minus 1 mod p. Okay, so now I'm getting somewhere, all right? If this -1 thing wasn't here, then I would just have y to the power of x. I could go look that up in my exponentiation table, okay? But first, I have to solve x to the minus 1, okay? So I have to figure out what is x to the minus 1. What modulus applies to x to the minus 1? Okay, so we think it's q minus 1, but let me take you down the road to that answer instead of just jumping to it. What is the modulus that I do on exponents? So if it's a base, I call this a base, like y is here, it's in the base, I do mod p. If it's in the exponent, I'm allowed to mod it by something, but it's not p. What is it? It's q, okay? All right, so this is going to be the same as y times x to the minus 1 mod q mod p. Okay? All right. Now, before, is this what we saw before? Not quite what we saw before. So what we saw before was I had x to the minus 1 mod q. Okay? What is x? Is that in the exponent or is that a base? It's a base. So I have a base number to the power of -1 in the exponent. Okay, so mod p is applying to the x and mod q is applying to the -1. Is that the same thing that I have here? No. So now I have all of x to the minus 1 is in the exponent. Okay? So I can do the same trick, okay? But what I need to do is I need to figure out what's the modulus for the exponent's exponent. And it has to be smaller than q, okay? So what I want to do is I want to say y to the power of x to the power of -1 mod something mod q mod p. Okay? So if I can figure this out, then I can solve this equation. And this is a little weird. It's probably the weirdest thing that you'll see today. It is something, though, that we will use in Planck. Okay, so we're going to use this idea of what's the group that's above the exponent kind of thing. Okay? All right, so what modulus could we use here? Okay, so we could try and look it up from the table itself. What I don't have, though, is I don't have a table for mod q. I could make a table and then we could look at it. I just have a mod p table. So if I had it at the fingertips, I would do that, and that's actually a great idea, but I didn't prepare that ahead of time. Okay, what we can do is we can use that theorem that we used last time from Fermat. Let me find it. Okay, what does it say? it says g to the p minus 1 mod p always equals 1. Okay? All right. So in our case, because we're in an exponent, the only difference is that p's become q's. Okay? But this relationship still holds. Okay. And also, when I went from P to Q, why did I go to Q? I went from P to Q because Q divides P minus 1. Okay, so remember Q divides P minus 1. And because I'm working in GQ, because Y is in GQ, everything has order Q, all the exponents. Okay? If I wanted to, though, let's say I wrote this. So I don't know what this is, but I just want to give you a little more intuition for what the answer is. Is this okay? So I do mod p minus 1 instead of mod q. It's going to be okay because q divides p minus 1. It's a waste of work because I could mod by something super smaller, but in this case, p minus 1 is a multiple of q, and so it will have the same effect, essentially. Okay. Now, when I went from mod p, I went to p minus 1. What do you think happens when I go from p minus 1 up? P minus 2. Okay. So if I want to go up an exponent, all I do is I subtract 1 from whatever it is below me. Okay. So here, what I can do, if I go back to this line, I can go q minus 1. Okay? Then I can do mod q, and then the whole thing is mod p. Okay? And so in general, that's always going to work. Okay? So I'm going to just put a little sidebar here, because this is an identity that we'll come back to. If you ever see a number that's like a to the b to the c, okay? A is done mod p, b is done mod q, c is done mod q minus 1. You could keep going. We're not going to ever keep going beyond that. Okay, so we'll go up 2 levels, and that's it, and then we'll stop. Okay. Okay, now that I have this in place, can I simplify this equation? So forget about the whole thing, just concentrate on this. -1 mod q minus 1. Okay, so q minus 2, why? Okay, so it's whatever the number is here minus 1. So we already have a -1 here. And so we're going to have another -1, so it's going to be q minus 2. All right. So in other words, whatever the modulus is, you can always add it to the number. It doesn't change it. So if I'm working mod 12, think of a clock. If I add 12 hours, it doesn't change the number. Okay? So another way of thinking of it is I'm just going to add a q minus 1 to the number. So I'm going to have q minus 1 plus -1. Okay, and that shouldn't do anything. It shouldn't change anything. Mod q, mod p. And so I'm going to have x to the y to the q minus 2. Mod q, and then this is going to be mod p. Okay, now can I solve this? So if I put in numbers, I can solve it. What I don't have is, I gave you an exponentiation table for mod p. I didn't give you one for mod q. Okay, so again, I should have prepared better. If I had it for mod q, we could do an actual numeric example. Then you could just look up whatever it is to the -2, and then you do a second exponentiation lookup in your mod p table. Okay, so it's 1 mod exp in like a mod q table, and then it would be 1 mod exp in mod p. Okay, so I didn't prepare the table, but let's do a numeric example anyways, and I'll just get Wolfram Alpha to solve it for us. So give me well, let's just use the same y and x. So I was calling y equals 8, x equals 4. All right, so example, x equals 4, y equals 8. Y equals a to the x mod b. Eight equals a to the 4 mod p. A equals 8 to the power of 1 over 4 mod p. A equals 8 to the 4 to the -1 mod p. Eight equals 4 to the q minus 1 minus 1 mod p. So we have 8 to the 4 to the q minus 2 mod p. The example we were using, p is 23, q is 11. So let's go ahead and, I could have filled those in right from the start, but I didn't. So I'm going to have 8 to the 4 to the 11 minus 2 is 9. Four to the 9, I'm going to take mod q, which is 11. And 8 to that answer, I'm going to take mod 23. All right, so 4 to the 9 mod 11. 4 to the 9 mod 11. Okay, like my notation. Okay, 4 to the 9 mod 11 is 3. This we can look because we have the table for it. So 8 to the 3 is 8 to the power of 3 is 6. Okay, so what's the moral of the story? The moral of the story is taking discrete roots is efficient. Okay? All right, so there's no problem doing discrete roots. So we can do discrete division, which is invert and multiply, and we can do a discrete root if we need to. Will we ever do a discrete root? Never again. Okay, so I'm just showing you just to be complete, but this is the last time you'll see a discrete root. If you study other crypto systems like RSA, where you're doing mod n instead of mod p, and no one knows the factorization of n, discrete root's not efficient. Okay, in fact, that's related to the RSA difficulty. Okay, but here roots are fine. If you need to do it, it's there. Okay, what's the other combination that we haven't done? So we've done y equals a times x. We've done y equals x times a. We've done y equals a to the x. Now we're going to do y equals x to the a. Okay, how do I solve this ignoring the mod p? How do I solve for a? Okay, we can do what we tried to do last time. What did we try to do last time? We can try and take the log of both sides. And what base do we want our logarithm to be? Base x. Okay, so let's try log base x of y equals log base x of x to the a. Okay, this will cancel out, and so we'll get a, and we'll be stuck though with the log x of y here. Okay, so I just same equation. I'm just going to move a to the left-hand side because that's what we were always doing. Okay. Is there any sort of exponents? Before, we always use the trick of like, I can't do division. Well, first off, can I just do a logarithm? If I do a logarithm, am I going to get an integer out for sure? Do logarithms tend to do they tend to give you integers, or do they tend to give you decimal numbers? Okay, they tend to give you decimal numbers. Okay, almost any time you do a logarithm of anything, you're almost never going to get an integer unless if it's like a perfect power between these two. Okay, so same reason I can't just do a root or just do a division. I'm going to bounce out of the integers. Okay, so what I need to do is, with division, I was able to substitute in a -1 to the power of -1. For roots, I was able to do x to the 1 over whatever the root is. Can I do the same thing here? Can I convert this into something about exponents? Then maybe I can reduce it down to something I can solve. So is there something that's identical to a logarithm, but it's just expressed in terms of exponents? So the answer is no. Not that anyone knows about anyways. Okay? So there is no equivalent exponentiation identity that's equivalent to a logarithm. Okay? What does this mean? What this means is that we actually can't solve this efficiently. Okay? So there's going to be no solution to this problem that's efficient. So we call this the discrete logarithm. Discrete because it's mod p. So anytime we do mod p, discrete is the term that we use. Discrete means like just integers, no decimals. We say, oh, it's discrete. So it's going to be the discrete there is no known efficient algorithm for solving it. And I'll add an important caveat, and I'll say on classical computers. What do I mean by that? What I mean is non-quantum computers. So one of the reasons there's a lot of excitement around quantum computing is that there is an efficient algorithm for solving this if you have a quantum computer. But for classical computers, we don't know. I can't say there isn't one. Maybe there is. Maybe someone here will think of it, and then you'll become very famous. But as far as we know, and people have been trying for at least 50 years just in crypto, but then maybe they've been studying it longer before it was applied to crypto, trying to find a solution, and they can't. Okay, there are algorithms for solving it. and some of them do a little bit better than just like scanning along a row. And I'll show you one. I'll show you the basis of one that we'll see when we're going to talk about something called commitments, and I'll show you actually how you can use commitments to solve the discrete logarithm problem in faster time than just scanning across a row. The problem is that you still have to scan across the root of a row, which is still going to be like way too big of a number. Okay, what else do I want to say about this? Okay, so there's known efficient algorithms on quantum computer. So how can you solve it? You could solve it through brute force. So brute force is what we'll do in a second. So we will solve it. I'll show you the solution to it, but it's because we scanned along a row. I can't do brute force though once the row gets too big. Okay, so once the row is bigger than I can search using a computer, then I'm out of luck. Okay. And so when does a computer stop being able to do it? Well, we don't know the exact point where it stops, but we take wherever we think it would not be able to do it, we add a bunch to it to make it a little bit bigger to give us like a conservative bound. And so what NIST will tell you, for example, is that P should be like greater than 4096 bits, greater or equal to. And I forgot to do this last class, but we should say the size of P, not the value of P itself. So that notation of the bars just means the size of P. So it's greater than 4096 bits, which is the same as saying 2 to the 496. And then if we use a safe prime, Q is going to be 4095. That's fine. So it's great for safe primes. But we can actually use a prime that's much, much, much smaller if we want. It makes things more efficient. But we'll look for about 256 bits here. Okay, so we're talking like really big P's. Then solving this, you just can't do it. Okay, and there are challenges too. So there's people that post, here's two numbers. It's literally this equation. They just say, here's the Y, here's the A, here's the P. And if you can solve it, then you get your name on. There used to be like money associated with it, but now I think it's just you get your name on it or whatever, and then they say, oh, you're the first person to solve it. And what they do is they release bigger and bigger P's. So they started with like, say, an 800-bit P, and then someone solved it, and then they have like a 1,000-bit and a 2,000-bit and things like that. And so there's a bunch of levels that have been solved. But when people solve them, they like take, I don't know, a bunch of PlayStation 4s because they have GPUs, and they like hook them all up to each other, and then they spend like 6 months like looking for it, and then they find it, kind of thing. So these are called challenges, but it helps us like understand where the bar is in terms of how fast you can solve these things, or how long do we have before this isn't big enough and we have to make it bigger.
So 2048 is definitely broken?
No, 2048 is still secure. So I think the highest that someone's probably done in practice is probably around 1,000 bits. But what we do, when NIST says this, they're thinking about like 30 years from now, kind of. So they're not comfortable saying, 2048, because like it's true today, but it might not be true later. Yeah. And if you encrypt with these things and it gets broken in 30 years, you're done, kind of. Yeah. The bigger threat to this whole thing is this quantum computing. Yeah. Now, by the way, you might wonder, what about Planck? I'm going to take like a whole course on something that's going to get broken by quantum computers in 2-3 years. And so the answer is that Planck, you can do it. I'm going to show it in a way that is not secure against quantum computers because it's the easiest to understand. But what you can do is you can take the one thing and just replace it with something else, and now it's quantum safe, as far as anyone knows anyways. And so there is, you're not going to waste a whole bunch of time. There is a way to make it post-quantum. I don't teach it the post-quantum way because A, it's more complicated, and then B, it's also like, people don't use it in real life because it's bigger. And so since we don't think we have a quantum computer coming anytime like in the next 2 years, 3 years, we'll just keep using the one that's efficient, and then when it looks looming that there's a quantum computer, then everyone's going to switch over to the less efficient ones. But anyways, I'll teach you. I'll show you both ways, or at least I'll show you like the black box that you can replace in order to make it post-quantum. Okay, so summary. We're going to see a lot of equations. They might be a little more, well, they will be more complicated than this, but this is like, you need to understand this equation, and you need to understand everything that's going on in this equation. There's only 4 numbers, but you need to understand them, okay? So when you see an equation that looks like this, the first thing is that you can't, I switched around the letters. So this is like a more standard way. So note that it's not the exact equation that I wrote here. What I'm calling A, actually I just turned A into G. That's all I did. Anyways, okay. So y equals G to the X. G is an element of GQ. Okay, so it's a generator. We use the word G because it generates GQ, but it just means that, actually, maybe before talking about this, let's start with P. Okay, so P is going to be a large prime. So think like 4096 bits. And there's going to be a smaller prime q that divides p minus 1. Okay, and q will also be prime, and q is going to be like 256 bits kind of thing. If we do a safe prime, then p minus 1 divided by q is 2. So 2q is p minus 1, or 2q plus 1 equals p. Then it's going to be 4095 bits, because it will be 1 bit shorter. But we might use a much smaller prime, and that's fine. Okay?
Sorry, what's written on top of the q there?
Here and, sorry, the word and, yeah. Okay, so we start with a prime, p. We have a smaller prime that divides p minus 1. Okay? And the q here, why do we have a q here? Why do we care about it? Well, that's the GQ here. Okay, so we're going to find a generator that creates this group GQ, which means that there's q, so the 256 bits prime, there's going to be that many of them, that many numbers in G. And GQ itself is closed under multiplication. All the rules apply to multiplication. You can invert, you can divide, you can do roots if you want. You just can't do logarithms. Okay? So that's it. Okay? Now, who gives you G, P, and Q? Usually you'll be given that. Okay? So we call it a public parameter. And everyone in the world can use the same ones. Okay? So we just really have to choose this once. So like NIST or someone will say, here's a P, here's a Q value, here's a G value, and now you're good to go. Okay? All right. X, what can we say about X? So it's mod Q. So what does that mean? What values can it take on? Okay, it can take on Q, 0 to Q minus 1. It can also take on values outside of that. It's just when we apply the mod Q, then it will get mapped back to that space. Okay, so it's 0 to Q minus 1. And there's a fancy way of writing it in math, which is we say the set of integers, Z, Q. Okay. So this is getting a little sloppy, so I'm just going to rewrite the same thing here. So P is prime. G is from GQ. x is from ZQ. Okay. And if you look back at our exponentiation table, you'll see that. So GQ are the rows in our exponentiation table. So this is GQ. And the columns are ZQ. Okay, so these are some integers. They're all less than p, but they're not every integer that's less than p. There's q of them. There's 11 of them. And they're all closed under multiplication, blah, 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 blah. And we can raise them to the power of anything between 0 and q minus 1, which is ZQ. What about y? What group is y from? Is y a prime number? Is it from GQ or is it from ZQ? It's one of the three. So sorry, just, it's either this, or this. So say it loud, sorry. So it's not prime. Okay, so it could be any number from 0 to p minus 1. So I'm just going to pencil that in. 0 to p minus 1. Okay. Could it be 0? What to the power of what would give you 0? Only 0 to the 0, which is technically undefined. But 0 is not part of GQ. We know that, yeah? So we can get rid of 0. And we can just consider 1 to p minus 1. So this group, I mentioned it last time, it's called ZP star. So that's the integers from 0 to p minus 1. The star means that you get rid of all non-invertible elements, which is 0. Okay. Do we think, so this is true. Y is in Z star P. Okay. It's not going to be something that's not in Z star P. But can we be even more restrictive? Can we say it's actually from, like, everything in GQ is also in Z star P, and everything in ZQ is also in Z star P. They're both like just smaller, they're smaller than Z star P. Okay, so what's the smallest thing I can say about Y? Yeah, so that's the quadratic residues, I think. Was it the quadratic residues? Okay, it's not related to that. The question is, it's coming across as like a really tough question. It's not that tough. Let's say I wanted to look up a g in the x. What table am I using? I'm using this exponent table, okay? Let me put it this way. Let me just write it down here. Y equals g to the x, just to remind ourselves. Mod p, and this is a table for mod p. Where are the where are the x's in this table? The columns. Where are the g's in this table? They're the rows, okay? So this up here, these are all the possible values of x. Okay, so these are all the x's. And these are all the possible g's that you can see. Okay, so for this equation, every g that you could put in here is right here. And every possible value of x that you could put in here is right here. Where's y? It's the grid here. Okay, so these are all the possible values of y, the white stuff. Okay, now, when you look at that, do you see every number between 1 and 22? Is the number 3 in that table somewhere, inside the white part of the table?
Yes.
Okay, point it out. Oh yeah, so sorry, it is. What about the number 5? No? What about the number 14? No? Okay, so what are all the numbers that appear here? If I were to write down all these numbers, sort them, get rid of all the duplicates, I would get GQ. Okay, so all the numbers that are here are the same numbers here. So all the numbers here are just one of these numbers here. Okay, why is that the case? Because GQ is closed under multiplication. If I take two things from GQ and I multiply them together, I'm going to get something in GQ. Okay, let me write that here. I said somewhere, I maybe didn't say it exactly. What's exponentiation? Exponentiation is just multiplying by yourself x times. So if g's in GQ, is g times g going to be in GQ? Yes, because I have two elements of GQ. I'm multiplying together. I can't leave GQ. Okay? Is g times g times g times g going to be in GQ? It will, because I'm multiplying a bunch of stuff from GQ together. Okay? So what will y be by necessity? It has to be part of GQ too. Okay? So I'm not choosing y to be GQ. It's just that because I chose g to be in GQ, and I'm just doing multiplications and exponentiations, I'm never going to leave GQ. Okay? Now, there are some operations I could do here where I leave GQ. The simplest is addition. Okay? So if I do g plus x, then I'm no longer necessarily in GQ. I'll stay in ZSRP, but I won't necessarily be in GQ. Okay? We're never going to do that. Okay? So you're never going to see additions unless if they're in the exponent. Okay? So you're never going to see additions down here. The only thing you're going to see are multiplications, or you're going to see exponentiations. Okay, so this is from GQ because G is closed under multiplication. And the other thing, I didn't write it down here, but I'll just note that the order of G equals Q, just if you ever need to know that. That just says that the number of elements in GQ is Q. Okay, so the discrete log problem, I'll just write it down formally, and then we'll move on. We'll apply it to something. And when I say formally, it's actually not even that formal, but I'll just write it down anyways. Okay, so given a large prime P with a divisor, actually let me where Q times some number plus 1 equals P. And Q is large. Not as large as P, but because it divides it. But Q is also large. Okay. Then it is infeasible to compute X from ZQ such that Y equals G to the X mod P for G from GQ. Okay, so it's sort of saying what we drew out, but it's just sort of putting it in the sentence. Okay. I'll just add what you're given. So you're given G, you're given Y, you're given Q if you need it, and you're given P. Okay, So I know what P is, I know what GQ is, I know what G is, I know that G is a member of GQ. I know what Y is. The only thing I literally don't know is X. I know it's some number between 1 and Q minus 0 and 1 Q minus 1, but I don't know which number it is. And so, yeah, so I want to solve it. Okay, now let's do an example. So we were doing, going back to this notation, 4 and 8. All right, so 8 equals 4 to the power of what? Mod P. Okay, now this you can probably solve just by looking at it, but let's go through the math anyways. So what I'm going to do here is I'm going to try and solve this. I'm going to use my exponentiation table, okay? And I'm going to say 4 to the power of something, I don't know what it is going to give me 8, okay? So what I'm going to do is I'm going to scan along the row. Yeah, sorry. Was there a question? No? Okay. So I want to find A. So I'm going to start at the row 4, and I'm going to look at every power 4 until I get 8. All right, so I start at 4. Am I at 8? No. Am I at 8? No. Am I at 8? No. Am I at 8? Yes. So what was the power that gave it to me? 4 to the 7 is 8. Okay, so A equals 7. But I couldn't do that directly. I couldn't just jump to the answer. I had to scan the row. And there's, as far as we know, there's no, there is a better algorithm than scanning the row, but you can't do much better than scanning the row. Okay, so A equals 7 is the answer, but it's because I scanned the row. I didn't just like sort of do like one exponentiation or one multiplication and get the answer. Okay, and so that's why it's going to be infeasible for a large table. Okay, so what we're going to do now is we're going to move on to an application of this. So I'll show you the first application, something that will be useful, which is called a commitment. Okay, so we have Alice and Bob. They're not together, they're not in the same room, they're talking on the phone. They don't have FaceTime or anything like that, they just have audio. And they want to play the game rock, paper, scissors. Anyone who knows what this game is? People are smiling, but I just want to, do I have to explain the game or does everyone know what it is? Anyone not know what it is? Okay, all right. Okay, so they're going to play rock, paper, scissors, but they're on the telephone. Okay, how are they going to play it? So they could both shout out what they're going to play at roughly the same time. But what if there's like delay on the phone or something like that, right? One of them could wait until they hear the other one say scissors, and then they say paper a split second later, and they could win that way. Okay, so what I want is I want a fair game where neither of them has an advantage of hearing it a slight second before the other ones. Okay, this works in real life too. I mean, you could be like really fast, and so maybe you win just because you're fast. But I want to have like a fair game of how to solve it. So we're going to use cryptography to solve it. Okay, so here's my idea. It doesn't quite work. We'll talk about why, but it's close. What Alice is going to do is she's going to pick one. So let's say she picks rock. And Bob is thinking paper. And let's first write in what could happen that goes wrong. Is Alice could try and say rock, and then Bob can say paper back. That obviously doesn't work because Bob saw rock, and then he chose paper just to win the game. Okay? So what we're going to do instead is we're going to put rock into a kind of envelope. Okay? So think of like a paper envelope. I put the word rock in it. I seal it and I give it to Bob. Okay? Bob can't open it. Okay? So he doesn't know what I played. And what Bob will do is the same. He'll put something, say paper, into an envelope. Okay? Now what can we say before we open the envelopes? What we can say is both of them are committed to their choice. They can't change it, okay? They've locked in what their choices are, okay? Does it matter which order you open the envelopes in? It doesn't now, right? Both of them are committed to their choices, and so you could open Alice's first, you could open Bob. Here, did it matter who said rock or paper first? It did matter, okay? The person who said first was at a disadvantage. But when we put it in an envelope, right? Does it matter who sends the envelope first? That also doesn't matter, okay? So by committing to things, what we were able to do is we were able to like make sure that like there's no fairness considerations anymore, okay? So then what can happen is we can open the envelope in any order. And now we can decide who won the game, and there's no fairness considerations anymore. Okay? All right, so what we need, we call this a commitment function. So the envelope here is functioning as a commitment function. And it's giving us two properties. Okay. Just tell me in words, in your own words, what are we looking for from the security? What is the envelope doing from a security perspective? Okay, say it louder. Like, hide. Okay, so it's hiding the contents of what's in the envelope. Okay, if it's a see-through envelope, does it work? It doesn't work. Okay. All right. So we call that hiding. So given a commitment to message M, it's infeasible and I'm going to start building up a little notation here. So we'll call the envelope C for commitment. Okay, so I'll just call that C. So given a commitment C to message M, so M's the message that goes in, C's the envelope when you're looking at it, it's infeasible to find M. Okay, the envelope's doing one other thing. It's not that easy to see what it's doing necessarily, but it is doing one other thing. People who've taken, say, blockchain with me might know.
Non-replication.
So very close, yeah? So, but what do you mean by that?
You can't really change your answer.
Okay, so that's exactly yeah. So once I put an R in the envelope and I give the envelope to you, could you possibly open the envelope and find a P instead? Or could I change what's in the envelope? Like let's say that Bob puts something in the envelope Then when we open the envelope, he sees that R is sitting in analysis, and he's like, oh man, I really wish I could put P in my envelope. Can he get P into the envelope somehow? He can't, right? It's too late, okay? So we call that property binding. So the commitment is bound to the value itself. So given a commitment C to message M, it's infeasible to open, or I'll use the word reveal, to reveal anything other than M from C. Okay, so we have a commitment function. We have these two properties. Now, there's a third property that is not strictly necessary. Okay, so this is an optional property. And it's called succinctness. And it says the size of C. How big is C? So if I put a piece of paper in the envelope has to be bigger than, it can be the same size as the paper or bigger, right? Succinctness says I can fold that paper up first and I can put it in a much smaller envelope. Okay, so there's some way of folding it up. Okay, so the size of C will be small relative to the size of M. Okay, what do we mean by small here? In practice, it could be a bunch of different things, but the main two categories that we see is something that's constant, so it's always the same size, or we see something that's called sublinear, which means it's smaller than linear. Linear is if the size of M grows, the size of the envelope is also growing at the same rate. Okay, that we call that a linear relationship. Okay, if it's M is getting bigger, C is getting a little bit bigger to sort of accommodate M, but it's not growing at the same rate, then we say it's sublinear. It's growing at a lesser rate. And so like logarithmic would be like a rate that would be common between the two. Forget about that for now. I'll show it to you like later when we need it. But for Planck, we're going to consider, we will have commitments that are succinct and they will be constant, meaning you can commit to like 1,000 rocks or 10,000 rocks and the size of the commitment will always be the same. The envelope will always be the same. Okay? And this is what's going to this is like the innovation and everything that we're doing is this succinctness property. Okay. In terms of the function itself, we basically have two things. One is I took something and put it in the envelope, and the other is I opened the envelope and showed you what was inside. Okay? So if we want to write it down as a function, we could say that we have an open function. Sorry, a commit function is putting it in the envelope. And then we have an open or reveal function. The commitment function will take some message M, and it will return to you a commitment C. The open function will take commitment C, and it will return to you the message M. Okay? All right. Now, envelopes are great, but this is sort of like a physical mail thing. What do we do in the digital realm? In the digital realm, we want the digital equivalent of envelopes, right? So what could we possibly use, say, from cryptography as our envelope? Any guesses at what that could be? Anything that you might have seen in another course, or anything you've seen in this course so far?
Signature.
Okay, we can think about a signature. A signature isn't hiding, so it is 100% binding, but it won't hide what's inside of it. Necessarily, it actually, that's sort of a technical definition, but it wasn't designed to do that.
Hash, that's fine.
Okay, so hash just by itself. If you have a hash function, that's an envelope. Okay, so a hash function is one way. So when you put it in the envelope, you can't pull it back out. It's hiding. And it has a property saying that you can't find collisions. And that basically says you're never going to find two things that hash to the same amount. So you're never going to be able to open it to something other than it. If you could do that, then you would find a collision. Okay, so hashes work. There is a small catch with what I just described, but I'll show it to you. What about from everything we've seen up to this point in this class? So we didn't talk about hashes in this class. But hashes is the right mental model. That's what's used in real life. Okay, what about the discrete logarithm problem? We just saw it. It said there's some stuff that's hard. Could we use it somehow to build an envelope? Okay, so we can try. So I'm going to show you what are sometimes called a Feldman commitment. All right, so C is commit of M. And so I'm going to define it as G to the power of the message mod P. Okay. Again, everything applies. G is from GQ, P is prime with Q as a divisor. M is a message. Here, to make this equation work, M needs to be an integer. Okay, specifically, it's going to be from Z star, or just from ZP, which is the integers from 0 to Q minus 1. Okay, if it's bigger than that, it's going to get modded down. Okay, now if I want to commit to the word rock, how do I do that? Well, I'm going to have to convert it to an integer first. Okay, or I'm going to have some convention that says, like, I'm just going to encode the number 0, 1, or 2. 0 means rock, 1 means scissor, 2 means paper, and then both Alice and Bob agree on that encoding. Okay, so if both of them know what it is, then I can use encodings themselves. And worst case, what I could do is I could use our friend the hash function. A hash function will take any data, it doesn't matter how big it is, and it will give you a short fingerprint of that data, which is something that's expressible in about 256 bits. And so we're always going to make Q big enough. Sorry, this should be a Q, not a P. We're going to make Q big enough so that any 256-bit hash output will fit inside of Q. Okay, so that's why Q is generally about 256 bits. So that's going to give us the ability to capture any message itself. Okay, so message M needs to be made an integer. And so there's different ways of doing it. You could encode it. It might already be an integer, like say it's ASCII text and you just convert it to hex and you say that that's an integer. So that's what I mean by encode. Or the other thing you can do is you can hash it. We didn't talk about hash functions, but there's something that exists there. Okay. What do we use for Plonk? In Plonk, we're not going to be committing to, we're never going to commit to text, okay? What we're going to do is we're going to commit to polynomials. And so they're already going to be numbers. And so this sort of discussion is irrelevant, but in general, this is what you would have to do. Okay. Now we need an open function. Okay. This is less of a function and more of a process. We can't directly open C without solving a discrete logarithm. So basically what's going to happen is you're going to just say, or I'll say give M and C. So you're just going to say, this is the M I used. They already have C, presumably, but if they don't, here's C. And then the person that's checking it will check whether it's true that C is G to the M mod P. Okay? So this is slightly different than, like another answer. So when I ask what could you use as a commitment, people sometimes think encryption. Encryption can be used as well. Okay, so when you encrypt the message, then that's like inside the envelope. And when you decrypt, you get back the message as well. A commitment is actually like simpler than an encryption because there's no key to get M back from C. So it's missing that operation. It's missing that decryption operation. And because we can't decrypt, all we do is I just tell you what's the value of C, what's the value of M. You re-execute it. So you commit to M yourself and make sure that it comes out to the same C. Okay, so that's how you check it. So it's kind of a cheap way of checking something. Cheap as in like you're sort of cheating somehow. It's not fancy. It's a very straightforward way. I just tell you what I use, and then you just check whether it matches. Okay. This is deterministic. So like as long as G and M are the same, you're always going to get the same value C out. Okay. So I'll just make a note of that. So what I mean is that this exponentiation operation, it's not like I do G to the M today, I get one answer. Tomorrow I do G to the M, the same G and the same M, and I get a different answer. Okay, it's the same. Just like any math equation, it's always the same. There's no uncertainty about what the result is that you're going to get. Okay, let's think about hiding and binding for this. Okay, so I'm going to start with the hiding property. Do we think that this commitment is hiding? Is there a way that you could look at C and figure out what M is? So I would solve for M. How would I figure out what M is? I would just solve for it. If I solve for M, what do I get? I get the log. Can I solve a log? I can't. Okay, that's the whole point. Okay, so hiding. Okay, so the first idea I have is I'm just going to solve for M. And in this case, I will be able to write down the equation. I'll get it's the log of C of G, log base C of G, but I won't be able to solve it. So discrete log problem, DLP, it's going to be infeasible. Okay, so breaking this commitment by directly solving for M is as hard as solving the discrete logarithm problem. It's exactly the same as solving the discrete logarithm problem. Okay. I'm going to leave space for one other thing I want to say about hiding, but before I say it, I'm going to go to binding. What can we say about binding? So let's say I commit to the message, whatever rock is. I take the word rock, I hash it, I get some integer here, and I compute G to that power, mod P. Okay, I give you C. Okay, can I open that to a different value M? So let's try and write down in math what we're doing, and then maybe we'll be able to see whether it's the case. So basically what happens is I have g to the m mod p equals c, right? And later what I want to do is I want to find m prime, so some different, so m prime, I'll put m prime not equal to m, so a different m. And what's the property I need? I need m prime to also equal c. Okay, the same c. So this number has to be the same. Okay, and all of these things have to be the same too. So it has to be the same p, and it has to be the same g, since that was defined. Okay. Is there more than one, or g raised to the power of something gives you c? Is there another thing that you could raise it to the power of and get the same c back?
Yes.
Okay, what, why, or give me an example, or whatever you might think.
Just like the mod table that it was repeating, right?
Okay, so let's look at the mod table, because that's where the answer is going to be. Okay, and so let's say that, let's pick a g. Pick a g. What's your favorite number here? 6. Okay, so this is my g. These are all the messages I could commit to. Okay, so these, I could commit to the message 0, and my c value would be 1. If I commit to the message 1, my c value will be 6. Okay, so these are the messages that I'm committing to, and these are the output of the commitment function c. Okay, so let's say I commit to the message 3. I get 9. Is there another message I could have committed to that also gives me 9? And why not? Or like, what are you looking at to confirm that? There's only one 9 in this row. Okay? There's only one 9. There isn't more than one 9. Okay? So once g is fixed, it's 6. 3 is the only thing that gives me 9. Okay? Is there any repeats, period, across this row? No. How many numbers are in this row? There's 11 of them. The numbers in this row correspond to GQ. There's 11 numbers of GQ, so every number here is every number here, and that's the way it's going to be, okay? So we also know that the reason we made this table, if we go back to the bigger table of P, is we said we went through a bunch of integers, we hit the number 1, and then it just repeated, kind of thing, okay? So there's definitely no repeats here. Okay, so what does that mean for binding? It means that mathematically speaking, there is only one M that gives you C. Okay? All right, so given, once you lock in G and P and all the other numbers, given G and P, there is only one M. Actually, I'll give you C as well. So we'll lock in C. So I'll give you G, P, C, and I'll say there's only one M for C equals G to the M mod P. And then I should also say that's true for all C's. So it doesn't matter which C I give you. There isn't some weird C, like we just checked that this one row in the table didn't have repeat elements, but what I'm telling you is no row has repeat elements. Okay, so it's not like, oh, there's an exception with 12. 12 happens to have the number 3 twice in this row. No, everything that's in this table, all the rows will have it. One exception is 1 here, by the way. So G, 1 to the power of anything is always 1. So another condition that we should specify is when we choose G, we don't choose 1. We call that degenerate. It's a degenerate case. So we choose some G that's not equal to 1. Okay, so let's try this. Let's try and play rock, paper, scissors this way. Okay? Again, there's something here I want to say, but I think an example will help us see it. P, 23. Q, 11. That lets us use our table. Okay? G is going to be a generator from GQ. Normally we choose the smallest one. That's normal, because usually you're searching for them anyways. Well, I shouldn't say that's normal. But anyways, we'll always use the smallest one. Okay? So the smallest generator is 2. So we'll say G equals 2. Messages. I have rock. I have paper. And I have scissors. I'm not going to do a hash function off the top of my head, so let's just encode these as integers, okay? So let's say that rock is 0, and we'll call paper 1, and we'll call scissors 2, okay? Doesn't matter, you can encode it any way. As long as Alice and Bob both agree on it, then it's fine. Okay, so here's Alice. Here's Bob. Alice is thinking, I think, rock. And Bob was thinking paper. Okay, so what does Alice send to Bob? So she's going to send G to the 0, right? So she's going to send G to the rock. So what's G? 2. Rock. Mod 23. We can go look it up in the table, but what do you think it's going to be? It's going to be 1, because anything to the power of 0 is 1. Okay. So she's going to send the number 1 to Bob. Bob is going to send G to the paper. So he's going to send 2 to the power of 1, mod 23. Again, we could go look it up, but what do you think the answer is going to be here? It's going to be 2. Okay. So basically, Alice sends the number 1, Bob sends the number 2. Okay. Then Alice says, I was doing paper. Okay. So I was doing 0. And I'll write it like this. I'll write it out slightly here. So this is like, we'll call this, sometimes we refer to the phases. So we call this the commit phase. So now they're both committed. This we call the reveal phase. So Alice will reveal that she had rock, and Bob will reveal that he had paper. And then we'll have a check or verify phase. I don't have to draw this. Okay, what Bob's going to check is whether she lied or not. So she's going to say, okay, Alice is saying that it was 0, so I'm going to check whether G to the 0 actually equals the number she sent, which is 1. Okay? And so in this case, G was 2, so 2 to the 0 does equal 1. So that's, Bob's happy. And then Alice is going to check, okay, he's saying that he did 1. The commitment I got from him is 2. So is G to the 1, does that actually equal 2? So G is 2, so 2 to the 1 indeed equals 2. And so Alice is happy. Okay. Now what if Bob lies here? So he says, there's no reason for him because he's winning, but let's say that he puts a 2 here, right? Then what Alice will do is she'll check whether 2 to the 2 equals 2. which it doesn't. So in that case, she'll catch him lying. Okay, this is great.
Of course, the weakness of this example is there's only 3 values, and so you know, even at the commitment phase, you know what it is.
Thank you. Brilliant. Okay, so I said there was something in hiding that I want to come back to. I said we couldn't solve for M directly, okay? But what if we guess M? Okay. In this case, there's only 3 M values, okay? I can put them all 3 through the commitment function. I can see what the result is. And if you send me a commitment that matches that, then I'm going to be able to know what you committed to, okay? Did I solve the discrete logarithm problem? I didn't, okay? So you can think of the discrete logarithm kind of as like, it's a one-way function. So I have inputs, I map to an output, I can't go backwards. But what I can do is I can always try inputs until they give me the same output, okay? So this works when M is small or feasible, or I'll say when the possible values of M can be guessed. So sometimes you might have no clue what someone committed to, like they committed to like a key or a password or something, and it's like I would have to guess that thing to even try to guess whether they committed to it or not. But for other types of things, you can, if you have some guesses, like in this case, it's either rock, paper, or scissors, then you can just try them all, and then you'll see which one was committed to, okay? So what that means is that this commitment scheme doesn't quite satisfy hiding yet. It's close, but because we have this guessing problem, it doesn't. And the reason why this guessing attack works is actually what we wrote up here, is because the commitment is deterministic. So every time I commit to the word rock, I always get the same value out. You commit to the value rock, I commit to this value rock, we get the same answer. And then we can compare them. And that's how I'm able to guess, okay? So my idea is, what if we do something exactly the same as this, but somehow we make it non-deterministic, so that every time I commit to something, I get a different value, then it's going to work, okay? Then I'm going to not have this guessing attack. And as long as I don't screw up the other properties that we have here, trying to make this non-deterministic, then it's going to result in a good commitment scheme, okay? So it's a consequence of it being deterministic. Some of you know about hash functions. If you do, I'll just say something to you. This is like a hash function. You can think of it as a hash function. It squeezes everything down to p, and it's hard to invert. It's not exactly hard to find collisions. In fact, if you just add p to this number here, you'll find collisions. But if m is already started from, if you're only choosing m's that are smaller than p, then it's perfectly collision resistant. There are no collisions mathematically, and it's also hard to invert. But if you know about hash functions, like say you have the hashes of a bunch of passwords, you can always guess them, right? You can build a rainbow table, you can try every single guess. Same thing applies to this commitment function. So you can just try every possible value until you find the right one, and then you know that you're done. Okay, so the next thing I want to do is I want to make this non-deterministic. And so I'm going to show you a second related commitment, but it's a little more complicated, called a Pedersen commitment. Feldman and Pedersen were cryptographers. Okay, so in the Pedersen commitment, what we're going to do is we're going to start the exact same way. Now, I want to make it non-deterministic. So non-deterministic means that when when I commit to the same message twice, I get different answers. Okay? How do you think we could maybe make this non-deterministic? How could we possibly have it so that, like, an exponentiation always gives you one answer. Like, g to the m will always be c, right? Like, there's no, like, exponentiation itself is deterministic. Okay? So in cryptography, there's two things that we can do. One is we can try and make the operations non-deterministic, but it's like really hard. Like basically computers don't work that way. Everything is deterministic. Okay? So what we do in cryptography instead is we just introduce randomness in the equation itself. Okay? So what the person committing to will do is they'll pick the message they want to commit to. They'll pick some randomness as well, and they'll mix that randomness in. Okay? So what we're going to do is we're going to introduce R, which is randomness, and there's different ways that we could mix it in, and we can think about the properties it has. So like, for example, we might just multiply the randomness in, okay? We could maybe we could exponentiate in the randomness, okay? And you can work through like whether these things result in a commitment function or not, but I'm going to show you what does work, which is I'm going to multiply it, not by the randomness, but I'm going to put the randomness in an exponent as well. So what I'm going to do is I'm going to choose a second generator, H. So G and H's are both generators, and I'm going to put the randomness up here. All right? So this is going to be randomness. And this will be a second generator. What's a generator? It's just something from GQ. Okay, so G's from GQ, H's from GQ. They generate GQ, that's why they're called generators. But anyways, we're just going to pick something else from GQ. Is C always going to be in GQ? Okay, if G's in GQ and H is in GQ, we're just multiplying them by each other, and so we're never going to leave GQ. So C is always going to be in GQ as well. Okay, so G will be in GQ, and C will also be in GQ. So it doesn't. So because, that's a good question though. Why doesn't it affect it? Well, R is going to be it's basically the number of times you multiply H by itself, right? So let's say R is 3, that means you multiply H by itself 3 times. Because H is in GQ, and because when you multiply things in GQ by things in GQ, you stay in GQ. Multiplying H by itself, it doesn't matter how many times you multiply it by itself, you'll never leave GQ. Does that make sense? Okay. And so R will be from ZQ. So it will be an integer between 1 and Q, just like M was here. So this is from ZQ. Okay. So and it's always the case. Every time we do things in the class, you have things at the base, they're always in GQ, and you have your exponents, and they're always in ZQ. The base is the rows, it's always in GQ. It's always going to be numbers like this. And the exponents will always be in ZQ. They're always just going to be the sequential numbers from 0 to Q minus 1. Okay, how much time do I have? Okay, all right, let's think about whether this is hiding and whether this is binding. Actually, before we do that, let me specify. I didn't fully specify it. So this is the operation that we were calling open. Okay. The only difference is it now takes 2 parameters. It takes a message and it takes randomness as well. Okay. So I'm going to open M and I'm going to open, I'm confusing myself here. This is the operation we call commit. So this is when I commit to it. It's going to take 2 parameters, M and R. Okay, the message and the randomness. We also need a way of opening this commitment. How do I open the commitment? It's going to be the same method as before. sorry, I'm going to open C. It's going to be a process, not an equation. What happens is I'll reveal both M and I'll reveal the R as well. Okay, so I'm going to reveal M and R. And then the person's going to check whether G to the M, H to the R actually equals the value C, which I'm trying to open the commitment to. Okay? All right, so let's do hiding and binding. Sometimes, eventually, I'm going to get lazy and stop writing mod P. Everything that we do will always be in mod P. So if I write something like this, just assume that it's mod P. Okay, I'm just writing it here just so you can keep looking at it. So what I can do is I can try and solve for M. So we had two strategies. I could solve for M. Or I can try and guess M. Okay, so let's go through them one by one. So solving for M, what am I going to do? So I got to move this H to the R kind of over to the other side. I don't know what H to the R is, okay? So it's going to be a little bit problematic, but let's just assume that for some reason I can split this whole thing on the right-hand side into the G component and the H component. Then to solve for M, I'm still going to have to take a discrete log. Okay, I'm going to have to take the discrete log G. It's just going to be a kind of crazy equation here. Okay, and so I don't know whether I can do this. I can even isolate it, but even if I could isolate it somehow, I still have to do discrete log. And this is going to prevent me from doing it. Okay, so this is still as hard as the discrete logarithm problem. It might be even harder because I might not be able to actually move this over to the other side. So it's infeasible due to the discrete logarithm problem. What about guessing M? Okay, so my idea before was I know it's either, M is either 0, 1, or 2, right? So I can commit to 0 and see what it comes out to, but now I have to choose a random number, okay? And if Alice, when she sends me the commitment to rock, her random number doesn't match my random number, am I going to get the same value or a different value? I'll get a different value, okay? So the only way I could find her value is I would have to know what randomness she used. Okay, so I'm not going to be able to guess it unless if I know what randomness she used. How could I know what randomness she used? Maybe she's using weak randomness, then I could potentially break it. But assuming that she's using strong randomness, the best I can do is try every random number. Okay, can I try every random number? How many are there? Well, there's Q of them, and Q is some 256-bit prime. I'm not going to be able to try every number. Okay, so this won't work because it's I would have to try every number. So I'll say if, just to emphasize it, infeasible if R is unknown and random, because then the best thing I could do is I could try every R. So it's infeasible to try every R. Okay, now there's something else I want to say here again. So I'm going to leave a little bit of space when it comes back to this. But yeah, I'm just going to skip it for now. Okay, binding. We'll talk about whether it's binding or not, and then I'm going to come back and say something about this here. Okay, do we think this is a binding commitment or not? So before I argued that once you fix C and G, there's only one M that gives you that C. Okay? All right? So here what I'm going to do is I'll sort of approach it the same way. So I'm going to say we're going to fix C, we'll fix G, we'll fix H, okay? And if we want to write the mod P, we'll fix P as well. So these are all like constant, okay? Okay, are there more than one values? In this case, I have two parameters I control. I can control M or R that give you C. Okay, it's a great question. Think about it in the background. I want to do a little review before we answer this question. G, where is it from?
GQ.
Okay. H, where's it from? Because G and H are from GQ, where's C from? How many possible values of C are there given that it's from GQ? Say loud. Okay, 11 concretely, but in general? Q or Q minus 1. Okay, so which is it? It's actually exactly Q. Okay, so there's going to be Q. So the number of C's, the size of C, I don't know how to write it. I'll just say that there's Q of them. That's what the subscript here means, by the way. Why do we write GQ? It means it's a group of order Q. A group where there's Q of them. Okay, so there's Q possible C values. Where's M from? What are all the values we can choose for M? So ZQ. Okay, so that's this, the columns. Okay, how many ZQ values are there? Not Z. There's Q of them, right? So ZQ, what does ZQ mean? It's fancy speak for the numbers between 0 and Q minus 1. How many numbers are between 0 and Q minus 1? Q. Okay. So ZQ, and there's, so that means there's going to be Q of them as well. I'll write all the groups down here. Where did R come from? Same. ZQ as well. All right, so there's Q M's and Q R's. Okay, so I have this crazy equation, and I'm going to simplify it by just putting it back in functional form. So I'm going to say it's the commit of a message and a randomness. The output of this, there's Q. How many inputs do I have? Well, I have Q choices of M, and I have Q choices of R. Okay, so I put Q M values in, Q R values, and I get out Q values. Okay, so here's the inputs. Are the outputs bigger or smaller than the inputs of all the possible values of the input? So because I have two inputs of size Q, how big is my input space? Q times Q. Okay, so I have Q times Q inputs. How many outputs do I have? Q. Okay, so it's going to look like this. Every input's valid, so every input will map to some output. What's going to happen because this is bigger than this? There's going to be some inputs that have to map to the same output. Otherwise, it doesn't work. Okay? So based on the fact that just strictly that because C is bigger than the output space is smaller than the inputs, there has to be collisions. Okay? So we call that a collision. Okay? What does that have to do with commitment functions? Are there more than one like MR values that give you the same C? The answer is yes. Okay? So this is a commitment function where you can open it up to more than one value. You can commit to rock with one random value, and then later when you want to open it up to paper, because that's going to win you the game, you can find a different random value that will allow you to open it up to paper. Okay? So binding, this is not a binding function. Okay? Now my hope for this is how easy is it to find that other pair? So I know now that they exist. Okay? How easy is it though for me to find it? Maybe this could still work if, for example, I would have to solve a discrete logarithm to find the other pair. Then this whole thing could work. Okay? But I don't know. Maybe it works, maybe it doesn't. All right? So what we're going to do is we're just going to pause here. And then next week we'll come back and I'll show you. Actually, what I want to do, the reason I want to pause here is I'm going to make a table that looks like this. I'm going to show you every value of the message and every value of the randomness. And then I'm going to show you visually what's going on. And I'm going to show you that even though you can break binding, you have to solve a discrete logarithm to do it. And I'm also going to show you that it's hiding. I'm going to say something else about hiding, which is that it has the property of actually being perfectly hiding, which means that even if someone could break the discrete logarithm problem, they can't break hiding as well. It's a property we won't use. It's just an interesting property. And then the third thing I'm going to show you is that if you can find two commits to the same message, you can actually use that to break the discrete logarithm problem. And so one of the algorithms for breaking discrete logs that's faster than just searching along the row is you just choose M's and R's at random, you figure out what the C is and you write it down. And if you ever generate the same C twice, then you can solve a discrete log. Okay, so I'll show you how that works as well. So those are the three things that will be on the agenda for next class. Any final questions? Okay, good. I'll see you next week.